Hi students, in the last class we had dealt with the grand canonical partition function and Q potential. We had also discussed about the different expressions of Q potential, like Q is equal to the natural logarithm of the grand canonical partition function, that is Q is equal to natural logarithm sigma rs e raised to minus alpha nr minus beta es. We had replaced sigma e raised to minus beta es with the canonical partition function qnr, so that I wrote the equation for Q potential as the natural logarithm of sigma nr equal to 0 to infinity qnr e raised to minus alpha nr. E raised to minus alpha was replaced with z, that is the fugacity, so that I got Q is equal to log sigma nr equal to 0 to infinity qnr z raised to nr, where qnr z raised to nr is my grand canonical partition function. So this was the final expression for the Q potential that we obtained. Q is equal to log sigma nr equal to 0 to infinity qnr z raised to nr. Now with this knowledge of the expressions for Q potential and grand canonical partition function, we are going to show the connection between the grand canonical ensemble formulation and the thermodynamics of any system under question. So we are going to discuss about the relationship between some of the thermodynamic quantities and the partition function and Q potential of the system. The first thermodynamic quantity that I am discussing is the average number of particles, that is n bar. N bar is equal to, we know, sigma rs n bar e raised to minus beta es minus alpha nr divided by sigma rs e raised to minus beta es minus alpha nr. So n bar can be found to be equal to minus dou by dou alpha of the log of the partition function, or it is also equal to minus dou by dou alpha of the Q potential. This equation can be very easily proven by substituting the values for QGC or the Q potential. You can very easily verify that minus dou by dou alpha equal to Q equal to minus dou by dou alpha equal to the log of the grand canonical partition function will give you the average number of particles. So we are going to discuss just the different forms of the average number of particles that you can calculate once you know the grand canonical partition function or the Q potential. So in the grand canonical ensemble formulation, what we are doing is we are trying to say that you just have to calculate the grand canonical partition function or the Q potential in order to determine the different thermodynamic properties of a system. So what we do is we are given a problem, and corresponding to that problem I calculate the grand canonical partition function or the Q potential, and from that I can calculate n bar using the following equations. So you can note it down, that is n bar is equal to, as I told you, the first one, minus dou by dou alpha log QGC equal to minus dou by dou alpha of the Q potential. Another form, n bar is equal to z into dou by dou z natural logarithm of the grand canonical partition function is equal to z into dou small q by dou z. N bar is equal to, another form, n bar equal to kt into dou by dou mu log of q capital QGC, that is equal to kt dou by dou mu small q. These are the different forms or different expressions or equations by means of which you can find out n bar just by calculating or determining the grand canonical partition function or the Q potential. In this slide, I am showing you the different ways to calculate the average energy E bar just by calculating or determining the grand canonical partition function or the Q potential. We know that E bar is equal to sigma Rs Es e raised to minus beta Es minus alpha Nr. Oh, there must be an additional term here, divided by sigma e raised to minus beta Es minus alpha Nr. So like that you can calculate the average energy. It's not simply this equation. There must be a divided by sigma e raised to minus beta Es minus alpha Nr, which I have missed out. Now that is the equation that is already known to us. That is, to get the average energy you have to find out Es into the probability distribution function. That is what we did here. But now we are going to just discuss the different equations by which you can calculate E bar from the if you know the grand canonical partition function or the Q potential. And those equations are given here. E bar is equal to minus dou by dou beta log of the grand canonical partition function is equal to minus dou small q by dou beta, and E bar is equal to kt square dou by dou t of log qgc, that is equal to kt square dou small q by dou t. So these are the different equations by which you can calculate the average energy. Next, we go into how you can calculate the Helmholtz free energy if you know the grand canonical partition function or the Q potential. We know A is equal to Helmholtz free energy. A is equal to Gibbs free energy minus P into V. Gibbs free energy is given by mu into n bar is equal to minus PV. Now this mu into n bar can be replaced by mu into n. For large systems, when the number of particles becomes very large, n bar can be approximately taken to be equal to capital N. Okay, with this information, I am going to replace everywhere n bar with n. And I am going to replace the entire term mu n bar in this manner. That is, z is equal to e raised to minus alpha. I am substituting for alpha. So z is equal to e raised to plus mu by kt. So log z is equal to mu by kt. Mu is equal to kt log z. And that kt log z I have substituted here in the place of mu n bar. Okay. So mu n bar is equal to kt log z into n. I have replaced n bar with n minus pv, or that can be written as nkt log z minus pv. nkt log z can be written as kt log z raised to n minus pv, and kt log z is equal to, we know q potential small q is equal to pv by kt, so I replace pv by qkt, or the final equation for A can be written as kt log z raised to n. I have missed raised to n here. Kt log z raised to n minus qkt, that is kt, and the potential q can be replaced by log of the grand canonical partition function. Okay, log of the grand canonical partition function. So this is the final equation for Helmholtz free energy. A is equal to kt log z raised to n minus kt log qgc. Next, we discuss the equation for entropy. S is equal to, we have written it from this equation, that is, we know Helmholtz free energy A is equal to U or E bar minus Ts. From that, I write down the equation for S. So S is equal to E bar by T minus A by T. E bar, we have already found out the equation for E bar as kt square dou by dou T of log qgc. So kt square by T gives me kt dou by dou T of log qgc plus k into log qgc minus log z raised to n. That is log kt dou small q by dou T plus, when I open this bracket, I get it as kq minus nk log z. So we have also got the equation for the entropy. All this involves just simple basic mathematics. So you will be able to solve all these relations very easily. So we have found out the thermodynamic relationship between the basic quantities, basic thermodynamic quantities, and its relation, how it can be determined from if you just know the grand canonical partition function or the Q potential. Next, and the last part of this discussion, we are going to see the application of the grand canonical ensemble. In the case of an ideal gas, how do you apply the grand canonical ensemble formulation in the case of an ideal gas? Now, the real power of grand canonical ensemble formulation becomes apparent or visible only when we study the problems involving quantum statistical effects and effects arising from interparticle interactions. But yet, here again, we simply try to solve the problem of an ideal gas using grand canonical ensemble formulation, and how we see how we get identical results as in the case we got when we solved for using canonical ensemble formulation and microcanonical ensemble formulation. So we begin by writing the canonical partition function here, that is Q is equal to, we know Q equal to Q1 the whole raised to n divided by n factorial. That is, we write on the partition function for a single particle in the ideal gas system divided by n factorial. Now, why do we write this n factorial? We recall the factor that the n factorial in the denominator arises because the particles constituting the gas are indistinguishable. If they are indistinguishable, it also means that they are not localized. If they are localized at a particular point or at a particular site, then they become countable or they become distinguishable. So, the indistinguishability means that they are non-localized too. Now, since our particle is not localized anywhere, then that means that they can move everywhere in the space available to them, or Q1 is directly proportional to the volume V. It is because, why, how did I write that Q1 is proportional to V? Because the particles in my ideal gas are indistinguishable and they are non-localized. They cannot be confined to particular sites. So, they are free to move in the total volume available to them. So, Q1 must be proportional to V. And it must also be a function of temperature. So, I represent my Q1 as equal to V into a function of T. So that I can write QNR as V into a function of T, the whole raised to NR, that is Q1 raised to N divided by NR factorial. Now we know the grand canonical partition function QGC is equal to sigma NR equal to 0 to infinity ZNR QNR, that is equal to sigma NR equal to 0 to infinity ZNR. I am replacing QNR with what we have got. Okay, so we got QGC is equal to sigma NR equal to 0 to infinity ZNR and this term here. Now I took Z inside the bracket, so I wrote ZV f of t by NR, the whole raised to NR divided by NR factorial. So I have got the equation for QGC as QGC equal to ZV f of t, the whole raised to NR divided by NR factorial. But we know that e raised to x is equal to sigma n equal to 0 to infinity x raised to n by n factorial. So I get QGC is equal to, can be replaced by, I think this summation is not needed there. It is QGC is equal to e raised to ZV f of t, that is e raised to x. Here e raised to x is equal to, here there must be the summation, e raised to x is equal to summation n equal to 0 to infinity x raised to n by nr. That is why summation nr 0 to infinity, this term divided by the factorial must be equal to QGC is equal to e raised to Z V f of t, or small q is equal to log qgc is equal to zv f of t. Now we have got zv f and t q potential in terms of this. So we can very easily determine all the thermodynamic quantities needed for us. First we find out what is N. N, as you all know, is given by N is equal to Z into dou by dou Z of small q. From that I get N is equal to ZV f of t by simple differentiation. Now you know q is equal to this we have got, but q is already equal to PV by KT. From that I can write down PV by KT is equal to this. Okay, so all these are simple informations that we get by regarding the ideal gas just by knowing the q potential. Next we can find out. Now I have got the equation for N, and N is equal to ZV f of t, but we already know N is equal to PV by KT, that is PV is equal to NKT. Now the internal energy of the system can be calculated using the equation E bar is equal to KT square dou by dou T of Q. Again KT square ZV f dash T. I have differentiated Ft with respect to time. So E bar is equal to KT square N f dash T by Ft. How did I get that? I just replaced Z with N by V f of t, so that I got my equation like this in terms of f of t by Ft. So for an ideal gas, we know f of t, that is the relation of the exact form of this function f of t, is given by 2 pi m kt by h cube the whole raised to 3 by 2. If I substitute it here, I am just going to check if I am getting the right answer as in canonical and microcanonical ensemble formulation. So if f of t, the exact form of this equation is like this, then f dash t, I have differentiated it and I found out what is f dash t by t, and on simplification I get E bar is equal to 3 by 2 nkt, the correct result for the average energy of an ideal gas. That means the method that we have devised out of grand canonical ensemble formulation is truly correct. So we are getting convinced about it. Okay. Next, we also know that Q is equal to PV by KT. From that I can write down the expression for pressure. Helmholtz free energy can be determined from the equation that we have just discussed, that is KT log Z raised to N minus log QGC. You just substitute it, you get the equation there. And entropy too, from the equation KT dou Q by dou T plus KQ minus NK log Z, we can find out the equation for S. Now we have already seen that E bar, or the average energy, has this form. From that I can find out CV. I just do dou U by dou T, so that NK is equal to, I can simplify it. I have just used the quotient rule to find out the derivative. So I get CV is equal to this. Now suppose I am saying that f of t is proportional to t raised to n. I don't know the exact form. Previously I had told that the exact form of the relation is something. In the previous slide I had told that the exact form of the relation is f of t is equal to 2 pi m kt by h cube the whole raised to 3 by 2. Suppose I do not know the exact form of the relation, how the temperature is dependent, how temperature affects my function, then I can simply write it as f of t is proportional to t raised to n. Then I get my E bar as n into capital N kt, and CV, you just substitute t raised to n in your answer for E bar, so that you get E bar equal to small n capital N kt, and CV equal to dou U by dou T is equal to small n capital N k. Here we know small n equal to 3 by 2 for a non-relativistic gas. Now what we can do is, from the equation for n, and from the equation for A and S, we can solve or we can eliminate the Z from, if you do, you will find that you can eliminate Z from the equations using equation 6, 8 and 9, and you will get the equation A and S only in terms of N, V and T. This will essentially complete our study of classical ideal gas. So it's a very simple procedure of how you eliminate Z from the equations for N, A and S by simple substitution, so that you get your answer only in terms of N, V and T. This will essentially complete our study of the classical ideal gas. So we have just discussed a simple example of how we use the grand canonical ensemble formulation to deal with the problem of an ideal gas. I hope this part is clear to all of you. If you have any doubts, please do contact. Thank you.